Okay, then I can start the class today. So, as we were continuing with the calculation of the performance uh, of the impulse turbine, so the performance related uh, to the blade and the stage and the nozzle. So that we will see. Now, in the last class, we have calculated up to the power developed. Now we will continue from that. So we have seen the okay. We have discussed up to the blade efficiency, up to the blade efficiency. So that is equal to blade efficiency eta B is equal to 2 into delta VW into U by V1 square, where delta VW is the uh, change of tangential velocity of the steam. So this delta VW is the change of tangential velocity of the steam. U is the blade velocity and V1 is the incoming velocity of the steam. So just to complete it, let us write. So what is that? Delta VW is equal to change of tangential, or this is also called whirl velocity of the steam or the fluid, that is the steam, that is steam here. So incoming and outgoing. So comparing that, that is the change, delta VW. Now, U is the blade velocity. And V1 is the incoming velocity of the steam. Incoming absolute velocity of the steam. Of steam. Okay. Now, we will see this is the blade velocity. Now we will see the stage efficiency. Also the blade efficiency. Now we will see the stage efficiency. Now what is stage? Stage is basically a combination of the nozzle and the blade. So stage efficiency means basically if I consider, yes, yes.
প্লেট মানে ওয়ার্ক ডান বাই দ্য প্লেট এইটা মানে কি?
Okay, বলছি। So what is stage efficiency? Now we consider that in any efficiency, we will basically address that in terms of what is the energy that is supplied and what is the energy that is produced. So in case of stage efficiency also, across the stage, what is the energy that was supplied and what is the energy that, or what is the energy that is converted to work. So in case of stage efficiency, we will see that. So in the stage, the work that is done by the steam divided by the work that was developed, or work that was there in the steam. So work, that means enthalpy that was there in the steam. So total energy compared to the total energy that was available in the steam, what is the work that is generated? So stage efficiency means this across the stage. So it is like this. If I consider that the stage, so here you see that this is the complete stage. Here you have one nozzle. So here it is the nozzle. And say, for example, this is say one. I'm sorry. Say this is the N. So it is nozzle. And here it is the blade. So it is B. And taking these two together, this is the stage S. So here blade efficiency calculation, while doing the blade efficiency calculation, what did we see? That the energy supplied to the blade and the energy that was converted as work. So that is the blade efficiency. So in the blade, what was the energy, what was the work done on the blade divided by the energy that was at the entry. So that means that was the energy available. So for blade efficiency, what we did basically, blade efficiency, in the denominator, we have the energy available at the entry. Entry means before entering the blade. So that is the energy available at the entry. That means that was the kinetic energy generated by the steam, kinetic energy generated by the nozzle. So that was available at the entry of the blade. So that was the total available energy. Now, out of that, some of the energy was converted to the blade, converted in the form of rotation of the blade. So that was available at the shaft. So on the top, you have the work done on the blade, and in the denominator, we have basically the work available from the steam. So that is called the blade efficiency. So here, work done on the blade. Now, who is doing the work? Steam is doing the work. So work done on the blade by steam divided by the kinetic energy supplied. That means the kinetic energy supplied, it was the total energy that is available at the entry. Now, kinetic energy of what? Kinetic energy of the steam. Who developed that? The nozzle developed that. Out of what that was developed? At the entry of the nozzle, there was high pressure and high temperature. It means it was having in the form of internal energy or intermolecular energy, that is enthalpy. So high enthalpy steam, now when it was allowed to expand through the nozzle, that high enthalpy was now converted after expansion in the form of high kinetic energy. So that was there at the entry to the blade. That means from the exit to the nozzle, that is the entry of the blade. Now at this point, high kinetic energy was available, but the total kinetic energy is not converted to the rotation of the blade. That means the sum of the kinetic energy was there even after the steam has left the blade. So therefore, the remaining energy was supplied to the blade. So therefore, work done on the blade divided by the total kinetic energy at the entry to the blade. That means kinetic energy supplied. So kinetic energy supplied. Supplied to the blade. Now, the thing is that we have to understand that work done on the blade. So why I am telling this? Because for a turbine, the blade is not doing the work because initially the blade was fixed and we are not primarily moving the blade and doing work by the blade. We are basically what we are doing rather is we are supplying the steam. Now as the steam is coming, it is impinging or forcing the blade to move. Therefore you see that primarily the steam is doing work on the blade. Steam is having the energy initially. Even if the blade was static, the steam was moving. So initially the steam was having the kinetic energy or the momentum, and now the momentum is transferred to the blade. Therefore, the steam is doing work on the blade, not the blade is doing work on the steam. So there should not be any confusion related to that. Because steam is coming with a high kinetic energy and high momentum. So now it has the capability to do work on the blade. Initially, the blade was static. Now, as the force is applied on the blade, now the blade starts moving. So that is the mechanism or that is the working of the steam on the blade. So the work is done on the blade. That there should not be any confusion. Okay. Because the steam was moving initially and now it is pushing the blade, and therefore as we know that what is the meaning of work done means some force is applied and at the point of application of the force that uh, there is a displacement. So we can calculate the work done and rate of work done will be the power. So here work done on the blade. Okay. And out of what? The kinetic energy, out of the kinetic energy that was available in the steam, part of that is converted to the work of the blade. So that means blade is gaining the kinetic energy and it is rotating. So that is the blade efficiency. Now what is nozzle efficiency? Nozzle efficiency, I'm sorry, the stage efficiency again. Stage efficiency is again, we will consider the whole stage, that means nozzle and blade together. Again you see that in this uh, whole stage, if we try to calculate the efficiency of the stage, there is the one that means the blade where we are getting the basically the energy at the shaft. So for the efficiency of the stage, we will write that is work done. Stage efficiency is work done on the rotor divided by the isentropic enthalpy drop. Okay, so stage efficiency. Stage efficiency is equal to
প্লেটটাতে মানে কোনো ওয়ার্ক ডান করছে না, শুধু স্টিমটা ওয়ার্ক ডান করছে, সেটাই প্লেটের মোমেন্টামে চেঞ্জ হচ্ছে।
of course blade is not doing work. In case of a pump or a compressor, the blade or the impeller will do work on the fluid. In that case, the energy from the motor will be transferred to the fluid via the blade or the impeller. So there the impeller or the blade will push the fluid and therefore it will do work on the fluid. for a pump or compressor, because there we supply energy to the fluid, and the energy of the fluid increases because we do work on the fluid and the fluid energy increases. Okay, so you see that for a pump, the fluid, say for example, if we lift the fluid or the water from a uh, underground reservoir to the terrace top reservoir. So what we do basically, by doing the work, we increase the potential energy. So that is the mechanism. Say for example, instead of using the motor, you can yourself lift the water by a bucket from the ground floor up to the terrace top reservoir and put that yourself. So in that case, you have to do the work, and where you are doing the work, that you are doing the work on the water, and the water energy is increasing as because its potential energy is increasing. Now the water has the capability of releasing that potential energy. If you open the tap, the water comes out automatically because the water has the potential energy. Now it can come directly by spending that potential energy, and it will be converted to kinetic energy. As you see that the from the tap, you get some velocity of fluid because of that head, that potential energy, extra potential energy that you have supplied either by yourself by using a bucket and putting the water or carrying the water from the ground floor to the terrace top reservoir, or by using a pump, whatever. So the target is to increase the energy or potential energy by doing work. So you are doing the work. So that is the principle. That is the means concept. In case of a turbine, say for example, you just do the opposite thing. You allow the reservoir to open, and on the opening of a tap you put a blade and the blade will rotate, so that will be a turbine. That is the water turbine that we see in case of say Pelton turbine. So in that case, what the water does, using its potential energy, it converts that first to the kinetic energy of itself. That means the potential energy is converted to the kinetic energy of the fluid itself. Then the kinetic energy of the fluid, that is the momentum of the fluid, will be now transferred as the momentum of the blade, and therefore the blade will rotate, and therefore there will be the rotation of the shaft. So these things should not be confused. The energy conversion. Okay, I think it is clear. Is it clear? Okay, okay. So you have to write carefully accordingly. That means wherever you have confusion, you first make that clear, then you write. Okay. Do not write anything just as you have read it from a book or from source. So first clarify that what is happening, what is the energy transfer, what where from the energy is coming and where is it is going, and what is the objective of the device. That means turbine is to produce work. Okay, turbine is to produce the work. So who is doing the work? The steam is doing the work first, and it is rotating the blade, and at the shaft you are getting the kinetic energy. And in case of a motor, which is actually moving or driving a pump, so motor is doing work on the fluid, and that means motor is doing work on the blade, and after that the blade will do work on the fluid. So that is the thing. Okay, so stage efficiency here. Huh? Please repeat once. একটু আস্তে আস্তে বলো, আমি পুরোটা শুনতে পাচ্ছি না। একটু আস্তে আস্তে স্লোলি বলো।
বলছি যে মোটরের ক্ষেত্রে ওয়াটার বাইরে ফ্লুইড হয়ে যাবে সেখানে, ওয়াটার বাইরে ফ্লুইড হয়ে যাবে।
হ্যাঁ, মোটরের ক্ষেত্রে ফর মোটর you see the thing, what is happening, where from the energy is coming. In case of a motor, the energy is coming from, that is say either a battery or some AC source, then it is moving the motor. So the rotating the motor. Now the motor is coupled with a pump. So the pump is now driven by the motor. So motor is doing work on the pump. So there will be always, you see, a conversion. You will see that whatever motor is doing work and whatever energy that it is getting, the blade or the pump is getting, there is a difference. So if the motor is supplying say 100 and the pump will get say 90, so in that case efficiency will be 90%, like that. So that means what, the energy is coming from a source and there it will diminish. Even if it does not diminish, so that means the principle is that motor is doing work on the pump, then pump will do work on the blade, pump will do work on the that means the fluid, and therefore the energy of the fluid will increase. Okay. Okay.
Yes, sir.
Okay. Stage efficiency. So it is the work done. Again, work done on the blade or the rotor. Means blade means what? Basically, there are a set of blades, and therefore the blades are mounted on the rotor, and therefore it is work done on the rotor. So in some sources you will find that work done by the rotor. So please correct that. Okay, because the rotor is not doing the work. The work is done on the rotor. Again, if you means just you have to understand what is the system. That is very crucial in case of in case of thermodynamics. That is very crucial. Say for example, if you consider the turbine, say this is turbine. Now at the inlet the steam is coming, and from the exit the steam is leaving. So here what it is doing, basically steam is coming with some energy and it is leaving some with some leftover energy, and in between it has done the work on the rotor. So in the case of a turbine, the steam is doing work on the rotor, and therefore the energy of steam decreases and energy of rotor increases, as the steam is sharing some of its energy to the rotor. Therefore if you simply consider the energy balance, first law, then what it says, that total energy in is equal to total energy out, right? So total energy in case of a steady flow system, so total energy in here must be equal to total energy out. So here in case of the steam turbine, here it is coming with energy, incoming energy of the steam, and here total energy is living in the form of two things. Here energy out one for steam, and energy out another by the rotation of the rotor. So it is energy out 2. That means here what, say if we write in terms of rate, because it is always constantly moving. So it is energy in is equal to energy out, rate of energy out, and here energy out in the form of basically two things. Energy out in the form of two things. Energy out dot 1, that is living with the steam to the condenser, and energy dot out 2, that is basically our turbine work. So W dot T, turbine, and this is going to the condenser, right? So you see that, of course, the steam energy is more than the turbine work, right? So there you can basically see what is the conversion. So now again, the in case of this analysis, we considered the turbine as the control volume. So this is the control volume. Now, if I consider that turbine is now rotating the alternator, so consider that there is an alternator now connected to the turbine, coupled to the turbine. Here is there is a coupling, say. Now the alternator now will rotate. Now who is rotating the alternator? Turbine is rotating the alternator. So in case of the alternator, if I consider alternator as the system, or the means, yes, system or control volume, whatever, although there is no mass flow to this uh, alternator, maybe if there is a cooling system, that is a different thing, of course. So for that cooling purpose also, there is some energy interaction. Now if we have alternator here, then for alternator, the turbine is doing work on the alternator. In that case, rotor is doing work, because the some of the energy of the steam has been converted or transferred to the rotor. Now the rotor has the capacity to do work. So it has gained some energy, and therefore it has the capacity to do work on the alternator. Now therefore it will rotate the alternator, because they are coupled. So as the steam has transferred its kinetic energy to the rotor, now the rotor will do work. Therefore, for this rotor as the system, for the alternator as the system, definitely we will say that work done by the turbine. So for the alternator, the work is done by the turbine, of course. But for the turbine itself, work is done by the steam. Okay, so always for thermodynamics, in case of mechanics also, say for example, if we have two objects, we have to carefully means understand or carefully see what is happening. Say for example, there are two objects, A and B. Now, if I consider A as the system, or the free, if when we draw the free body diagram, that means that is the object under analysis. So if we consider this as the system, then what is the work either done on this or by this, that we will consider. So what we do, basically all the forces acting on A we consider, and therefore the resulting motion in terms of the acceleration, and then integrating that to get the velocity, and then integrating that to get the displacement, or means maybe it is a linear acceleration, linear velocity, linear displacement, or angular acceleration, angular velocity, angular displacement, whatever. So that we calculate by properly selecting the system or the object. That will give us the proper means selection of the system of forces that is acting. So that is why, means while telling all these things, quantities, we have to understand first that what is the system or what is the device we are talking about. Then only it will be correct. Otherwise, that will not be possible at all to say what is that, what is happening. So means unless we actually know what is the system, then it is meaningless to say that work is done by this or work is done on this. Okay. So it is appropriate only when we actually have selected the system or the control volume. Okay, that is very crucial. Without that, nothing has a meaning. Okay. For a turbine as the system, the steam was doing the work. That means steam was doing work on the turbine. Now, in case of alternator, the turbine is doing work on the alternator. So nothing is absolute. Everything is relative here. Okay, clear? Yes. So now, let us see what is that stage efficiency work done. In the case of the stage also the work is done on the rotor, and it is if isentropic enthalpy drop, because across the stage there is isentropic enthalpy drop. Now that is also happening in the nozzle itself. Okay, so let us re-look into that. Here you see that this is the whole stage. Now here the work is available from the rotation of the blade. So work done on the blade by the steam. So that is the mechanical power that is developed. And here across the stage, there is some enthalpy drop. That means what? The fluid was having at the entry of the stage, fluid was having some intermolecular energy, that is enthalpy. So after that means as it leaves the stage, it will leave with some enthalpy. Therefore, there will be a drop of enthalpy across this stage. So the stage efficiency is describing that out of the total enthalpy drop that is happening across the stage, what is the mechanical power that is developed? That means out of this total expenditure, how much is the actual gain? So expenditure means that is the drop. That means as if you have spent this much of money across this stage, and effectively how much power you are basically getting. The power is you are getting here only. And the enthalpy drop actually takes place in the stage. That is the enthalpy drop here. Okay. So that is the thing. So across this stage, that we can write the enthalpy drop is so delta H. So we can write that it is equal to now.
যেখানে এনথালপি ড্রপ তো ইম্পালস টারবাইনে একমাত্র হচ্ছে যে আমরা নজলই হবে, প্লেটে তো এনথালপি ড্রপ হবে না।
Actually, in the blade, there is only kinetic energy that is converted. So part of the enthalpy drop will be there actually. So enthalpy drop, although we consider that enthalpy drop, there is no pressure change. Okay. So there is no pressure change. Uh, so actually enthalpy drop is converted to pressure change. Okay. Now, if I consider that the pressure is high pressure is converted to the enthalpy initially at the nozzle, and that total enthalpy I'm sorry, the high pressure, that means enthalpy across that initially the high pressure is converted to kinetic energy. So here basically before that there was only basically in the form of enthalpy only. Now after that what is happening, that enthalpy is converted to the enthalpy drops, and the enthalpy is converted to basically kinetic energy. So here, so enthalpy drop, most of the enthalpy drop takes place here. Now therefore basically what is happening, the enthalpy is converted into kinetic energy. Now the kinetic energy that will change. So you are right, the enthalpy drop will take place on only in the nozzle. Enthalpy drop will take place only in the nozzle. Yes. There is no pressure change. The condition is same, only it is diverted. Okay, the kinetic energy, now what happens, the kinetic energy is converted to the kinetic energy of the blade. So there is no pressure change here, and we considered that that there is no if we consider that there is no change of temperature also, then it will be basically a uh, uh, means enthalpy will not change across this. Now, if means I have to, one thing I have to confirm that here basically if there is a change in temperature due to that, although there is no expansion, so I think it should be same. But across this, there is means after doing the work, it is not expanding, and truly speaking, physically, there should be some change in enthalpy because I think after doing the work, even if the pressure is not changing, uh, even if the pressure is not changing, if the temperature drops, uh, thermodynamically, I think the enthalpy will not change as if we draw a thermodynamic diagram, a TS diagram, if we consider that there is no frictional loss, etc., then from the exit of the nozzle, as the pressure is same, also the entropy is same, so the temperature will be also same. So if the pressure and temperature for a superheated vapor remains same, then the temperature should be same. From the thermodynamics, that means equilibrium thermodynamics, at the entry and at the exit, if the pressure as well as the entropy remains same, then the temperature will be also same. In that case, enthalpy will remain same. So the enthalpy will change only in the steam. Okay. Only in the nozzle. Okay. So therefore, actually this requires time to discuss all this. So let us go into our calculation. So stage efficiency, work done on the rotor divided by the isentropic enthalpy drop across the stage. Across the stage. But I encourage you to ask question so that uh, the concept would be actually clear. Because many things are already there in the book, so means all these definitions are there in the book, but discussion on the concept is more important, I think. So you can definitely, you will ask questions. Isentropic enthalpy drop across the stage. Okay. Now therefore, what is there? So what is work done on the rotor, that we have just seen. So work done on the rotor, what is that? That is power, say rate of that power developed. What is that? That we have seen. This one. That is the work, right? M dot into delta V W into U. Divided by enthalpy drop, that is basically M dot into delta H isentropic. You can write actually this as small delta H because mass flow rate we are adding. So it should be delta H means basically the specific enthalpy. Now, what we can do is we can write this as a product of, you see that m dot into delta V W into U divided by the kinetic energy of the steam after the exit from the nozzle. So half m dot into V1 square multiplied with half m dot V1 square. Now we are just multiplying and dividing. And it is here. So m dot into delta H isentropic. Now you see the meanings. The first quantity is what? That we have just developed. That is this one. That is blade efficiency. So 2 delta VW U by V1 square. After cancelling, obviously, the mass flow rate. So it will be 2 delta VW U by V1 square. And therefore, this is basically the blade efficiency. Therefore, if we write, it is equal to blade efficiency. So this is blade efficiency. And what is this basically? This is defined as the nozzle efficiency, because what is the meaning of that? For a nozzle, out of the enthalpy that was available, the steam has undergone an expansion, and spending that enthalpy, the kinetic energy was gained. So here that is the kinetic energy gain divided by the total enthalpy drop is the nozzle efficiency or the efficiency of the nozzle. So here that means kinetic energy gain is taking place in the nozzle. So that is the objective, to generate kinetic energy of the steam in the nozzle, and out of what that it is getting, out of spending the enthalpy. So out of spending the enthalpy drop, the steam is getting the kinetic energy. So kinetic energy developed divided by the enthalpy change or enthalpy drop, that is nothing but the nozzle efficiency. So this is nothing but the nozzle efficiency. So therefore, the stage efficiency is the product of the blade efficiency and the nozzle efficiency. Okay. Earlier, during the discussion on compressible flow, we have also discussed the nozzle efficiency. So actually, in that discussion, we told that nozzle efficiency, that is isentropic efficiency of the nozzle, that was uh, calculated as isentropic enthalpy of the nozzle. That is, for isentropic enthalpy, that was actual enthalpy drop divided by the isentropic enthalpy drop, or S you can write simply. So you see that basically, if it is not isentropic process, then there will be basically some loss due to friction. So what will happen due to that? There will be a increase in entropy, and the actual enthalpy change will be less compared to the isentropic enthalpy change, and therefore the actual velocity that would have been obtained at the exit will be less compared to the isentropic situation. So that was defined during the discussion of the nozzle efficiency, during the discussion of the compressible flow. If we write from the first law, then means from the analysis, then it will be seen that basically these two are same. This nozzle efficiency in terms of either kinetic energy or in terms of the actual, that is actual enthalpy drop, basically they are same. If you write from the first law, then since this is adiabatic situation, there is, and also that is involving no work interaction. So only way the enthalpy change is related, the only way the enthalpy change is there, it is related to the velocity change. So for isentropic process, there is no loss, but for an actual process, there is a frictional loss. So due to frictional loss, some enthalpy will be lost, and the kinetic energy will be developed that is less than the ideal situation. Okay. Now, we will now try to calculate the quantity, that is the maximum efficiency. Okay. What is the maximum blade efficiency that we will calculate?
ডেলেজ এসি মানে কি বলেন ওটা বলবেন? ডেলেজ এসি বাই
Actual.
ডেলেজ এসটা কি বললেন?
Actual. This is actual. For a nozzle, this is actual.
আচ্ছা, এটা
For actual process. This is actual. Actual enthalpy drop. And this is isentropic enthalpy drop. And what is the cause of this deviation? Due to friction.
অ্যাকচুয়াল মানে স্যার আমরা প্র্যাকটিক্যালি যেটা হচ্ছে ফ্রিকশন নিয়ে।
Exactly. Due to friction, delta H actual is less than delta H isentropic. Actually, isentropic means you can write IS or AS, whatever, means no issue. Same thing. You can write IS or S, means S means basically it is isentropic, constant entropy. Okay. So this due to friction, but the process is adiabatic, means in the nozzle the process is adiabatic, but there is a friction, so there is irreversibility, and due to irreversibility, there is entropy increase because the heat generated due to the uh, friction that cannot be released because of adiabatic situation, and therefore the entropy will increase. And here the actual enthalpy drop will be less compared to that in case of the isentropic process. And therefore kinetic energy gain will be less compared to the isentropic process. Okay. Now we will determine a condition, that is condition for maximum efficiency. Okay. Now we can rewrite. So if we write this, say what is blade efficiency? Blade efficiency is 2 delta V W U by V1 square. Now, what is delta V W? Delta V W is, you see, delta V W, if we see that triangle, delta V W is the change of the tangential component or the wall component of the uh, fluid. So it can be written as, if we write in terms of the blade angles, okay, because blade angles are the ones which actually are fixed. So if we write in terms of the blade angle, then it will be seen that what is that delta V W from this to this? That means this to this. Therefore, what is that? That means from the tip of uh, the velocity of the either blade, or that means either the velocity of the absolute velocity of the steam or the relative velocity, what is whatever is that. So this is the tip, and this is the tip of the another absolute velocity or the relative velocity, both are merged here. So from this to this, so that is the change of velocity. So that is a change of velocity in the world direction or the tangential direction. Okay. So what is that? Therefore, this is VR1 cos beta 1 plus VR2 cos beta 2. So this is this part, it is VR2 cos beta 2, and this is VR1 cos beta 1. So therefore, delta VW is equal to VR1 cos beta 1 plus VR2 cos beta 2. Okay. Now, if we just take this out, say VR1 cos beta 1, then it will be 1 plus VR2 cos beta 2 divided by VR1 cos beta 1. Okay. Next, we will define certain quantities like a blade speed ratio. We will define blade speed ratio as blade speed ratio is equal to rho is equal to the speed of the blade, that is u, divided by the speed of steam at the inlet, that is v1. This is known as the blade speed ratio. There is another quantity that we will define as cos beta 2 by cos beta 1. We will term this as C, that is cos beta 2 by cos beta 1. That is for simplicity, we are defining this. And another quantity that we will define. Now see that for a symmetrical blade, C will be 1. Another quantity that we will define as equal to the friction coefficient K as equal to VR2 divided by VR1. Friction coefficient means if there is friction in the blade, VR2 will be reduced from VR1. Otherwise, in the last class, I told that if there is no friction, then VR2 will be same as VR1. Even if the blade angles are different, the relative velocity will remain same for a frictionless blade. But if there is friction, then definitely due to friction, the velocity at the exit will be less. That means relative velocity at the exit will be less than the relative velocity at the inlet. So friction coefficient K is defined as the relative velocity at the exit divided by the relative velocity at the inlet. Again, for no friction, K will be equal to 0. I'm sorry, K, let me, means in that case, basically it will be 1. Now, let us write. Therefore, again, what we know is what is VR1 cos beta 1. In the last class, we have seen VR1 cos beta 1. In the last class, we have seen VR1 cos beta 1. You see this one is equal to V1 cos alpha 1 minus U from this. VR1 cos beta 1 is equal to V1 cos alpha 1 minus U. That VR1 cos beta 1 means what? Basically, VR1 cos beta 1 means basically the component of the relative velocity along the tangential direction. So you see that VR1 cos beta 1 plus U is equal to V1 cos alpha 1. That means out of the total tangential component of the velocity, part of that was due to the relative velocity and part of that was of the blade velocity. So therefore, the component of the tangential velocity of the relative velocity, component of the relative velocity in the tangential direction is equal to the total tangential velocity in the total tangential velocity due to the absolute motion minus the velocity of the blade. So I repeat, the the tangential component of the relative velocity, this one is equal to the tangential component of the absolute velocity at the inlet minus the blade velocity, because blade is only moving in the tangential direction only, so that is the quantity. So that we are writing, because you see that here now we are trying to convert this, you see, in terms of the quantities that are more important. So here we will write, so every step should be understood properly, that why we are writing this and that. So here it will be V1 cos alpha 1 minus U, okay, multiplied with 1 plus, now VR2 by VR1 it is K, that we have just defined K, and cos beta 2 by cos beta 1 is equal to C. That we have just done. Now here you see that I am writing in terms of V1 alpha 1, because V1 is the exit velocity from the nozzle. So that can be calculated easily if I know the enthalpy drop, and alpha is the nozzle angle, that is a design parameter that is known, and blade velocity, that is actually giving the power of the blade. So these quantities are more basically design related, means more basically known compared to the other quantities. So this is the instead of VR1, basically instead of VR1, this V1 is more known. Okay. Therefore, we can write this. So that is delta VW. Now, therefore, if we write what is the blade efficiency, what is blade efficiency here? Therefore, simply 2 U into delta VW, that is this one, divided by U1 V1 square. So delta VW we can write here V1 cos alpha 1 minus U multiplied with 1 plus KC. Okay. Now we will write here one quantity. I will multiply this one V1. You see there are two V1. Since I have defined rho as U by V1, so I will multiply this V1 inside, so that I will get a quantity of rho inside also. So that I will do. And this another V1, it will cancel with this one. So that will be a wise thing to split this V1 square into 2, that is V1 multiplied by V1. I will keep one V1 with this U and another V1 here, so that one V1 cancel, another it will be U by V1, that will make it rho. So it is 2 U by V1 multiplied with cos alpha 1 minus U by V1 1 plus KC. C. Okay. Therefore, it becomes 2 rho cos alpha 1 minus rho 1 plus Kc. Okay. Or if you just write, it is 2 rho cos alpha 1 minus rho square 1 plus Kc. Same thing. That is basically the blade efficiency in terms of this parameter that we have just defined. Okay. Next, you see that for a particular blade, the friction coefficient is known, the blade angles are known, therefore the quantity C is also constant. That means 1 plus Kc, this is constant. Okay. Also, alpha 1 is also constant because the nozzle is having a particular angle. Therefore, the blade efficiency depends on, for a particular set of stage, the blade efficiency depends on rho only. What is that rho? The blade speed ratio. It depends on the blade speed ratio only. So that is to be clearly understood. Okay. So it depends on the blade speed ratio only. Sorry. Okay. Because for a particular design, the value of 1 plus Kc is constant. For the blade, C is known, that is cos beta 2 by beta 1. K is also, that is friction coefficient for a particular blade, that is known. And alpha 1 is the nozzle angle, that is also known. Therefore, it varies, the blade efficiency varies with the blade speed ratio only. Okay. Now, therefore, we will try to calculate what is the dependence or what is the condition for maximum efficiency. Therefore, for maximum blade efficiency, d eta b by d rho should be 0. So let us calculate. So therefore, from this, what is that? D eta b by d rho. As this term is constant, so it is the differentiation of this only. So 2 multiplied by 1 plus Kc, it will not change or under differentiation. So it will be basically d rho of rho is 1. So it will be cos alpha 1 multiplied by d rho, that is 1, plus, sorry, minus, it is 2 rho minus 2 rho. Okay. So that is equal to 0. Now this is something which cannot be 0, right? It cannot be 0 because C or K can never be negative. So it cannot be 0. Minimum value will be basically 1. So it cannot be 0. So therefore, from this we can write that cos alpha 1 minus 2 rho is equal to 0 because one plus Kc cannot be 0. Therefore, you can write that the condition for maximum efficiency or minimum efficiency, we have not proved yet. So rho is equal to cos alpha 1 by 2. For maximum or minimum condition, we have to check whether the double derivative is negative. For maximum blade efficiency, as we know that this is positive, this is 0, and d2 eta b by d rho 2 should be negative. So what is that? d2 eta b by d rho 2 is equal to 2 1 plus Kc. It will remain as it is, and within this uh, cos alpha, so it will be under differentiation, it will be 0 because cos alpha is constant, it will be 0, and minus 2 rho, it will be minus 2 and after differentiation. So it will be therefore, what is that? So minus 2, I'm sorry, minus 4, minus 2 into 2, 1 plus Kc, that is minus 4, 1 plus Kc, which is negative, obviously, 0. Therefore, this is the value for which the efficiency is maximum. Therefore, we say that this is the optimum blade speed ratio. That is cos alpha 1 by 2. That is the optimum blade speed ratio. This is optimum blade speed ratio. For maximum blade efficiency. So we can write here that it is maximum. Therefore, that is the condition of maximum efficiency. So optimum blade speed ratio for maximum efficiency. That is called optimum because we have not seen that whether it is that means the blade speed ratio is maximum or not. This is not maximum. It is the condition for maximum efficiency. So we are calling this as optimum because the blade speed ratio can be more than that, can be less than that. So that is not the maximum blade speed ratio. That is the optimum. That is the condition for maximum blade speed, maximum efficiency. That is why we are calling this as optimum condition. Okay, this is for a single stage impulse turbine.
Multi-stage impulse turbine মানে তো compounding.
Exactly.
সিঙ্গেল স্টেজ ইউজ করা হয় প্র্যাকটিক্যালি?
না।
ঠিক আছে।
Because that in that case the velocity will be very high. During the discussion of the compounding, what is the necessity of compounding? During that we elaborately discussed that due to the single stage, the turbine speed will be very high, maybe of the order of 30,000 RPM. And if the speed is that high, then actually there is no practical use of that. No such machinery are there which can be rotated or which are need to be rotated at 30,000 RPM. One thing. Another thing is that if the turbine rotates at that high speed, then due to the centrifugal action, the blade and the rotor will have high vibration, maybe with a slight unbalance or imbalance of the rotor. There will be high vibration, and also there will be high centrifugal force on the blades, and the blades may break. Okay, and also that means at the exit there will be high carryover loss. So it is not wise to use a single stage expansion, because with a single stage expansion that is not economical, and also means in terms of the technical things, that is also not possible to control. Okay. Okay. So therefore, we can write that is rho optimum is equal to U by V1 optimum is equal to cos alpha 1 by 2. Okay. Now one thing I will tell here, that the angle is of the order of, that is nozzle angle, is of the order of 18 to 22 degree. Okay. Now, in that case, cos alpha 1 by 2. That means what is cos alpha 1? Can you tell? Say, for example, if it is 20 degree, if alpha 1 is 20 degree, what is cos alpha 1? Can someone calculate and tell me?
Sir, the value will be 0.9396. 0.9397.
0.9397. Okay, cos alpha is this
Nine.
one. Okay. And therefore,
Say cos 20.
so what is cos alpha? And therefore, what is cos alpha by 2? That is, in that case, what is rho optimum? Cos alpha by 2, it is about 0.47, isn't it?
Yes, sir. 0.46947.
469, exactly. 469. So this is the optimum speed ratio for a nozzle or nozzle angle of 20 degree. 20 degree. Okay. So one thing is that this is the optimum speed ratio. Now, if alpha 1 is say, if alpha 1 is say 90 degrees, I'm sorry, if alpha is 0, I'm sorry, not 90, not 0. If alpha is 0, then if alpha is 0 degree, then cos alpha is 1, and therefore rho optimum will be half. That means, for that case, what is the case? Alpha 0 means what? In that case, basically, we are considering a blade like this. And, I'm sorry, we are considering a situation so we are considering a situation where basically the fluid is
Yes, sir.
coming.
VR on and U are parallel.
Hmm?
VR on and U are parallel.
Exactly. Here, basically, the fluid is coming like this and it will leave like this. And the blade will have a velocity, definitely tangential. So, what is the condition? Therefore, the blade speed is half of the steam speed at the inlet. So that means here, for maximum efficiency, I'm sorry, yes. For maximum efficiency, this V2 will be VW2 will be 0. Okay. So this is VW2 means V2 will be, it will be leaving with, if it is coming with, that means incoming velocity, so it is V1 and it is U. So U will be basically V1 by 2 and the tangential component, this is 0. Tangential component of the velocity that is leaving, it is 0. Now, it is 0 in case of whatever be the angle. Okay, it is 0. That means the tangential component should be 0 for maximum velocity. Sorry, maximum efficiency. That means what is the condition? Here it is, that means for maximum blade efficiency, the outgoing fluid will have 0 tangential component. So this will be 0. That means the fluid will basically leave with alpha is equal to 90 degree, alpha 2. That
only
means
axial component.
it is only axial component. There will not be any tangential component. So during the, that means for alpha 1 is equal to 0, this is exactly half. Okay. For alpha 1 is equal to 0, this is exactly half. That means this length of U is half of this. Okay. And it will leave with 0. That means the total energy that is coming here, half of that, the total kinetic energy that is here, the velocity will be half of that blade velocity. And this will leave with 0 tangential component. So for maximum, this is for alpha is equal to, alpha 1 is equal to 0. Even if for, so no tangential component. Okay. So this is true for this also. So here also alpha 2 will be basically 90 degrees. For maximum efficiency. No world component of velocity or no world velocity component. Okay. Now, since it will have 0, that means if it is purely coming in like this, now actually, if there is no friction, we know that the relative velocity is also tangential. That means relative velocity also tangential at the inlet as well as at the exit. Now, since there is no tangential component, therefore the velocity at which the steam will leave, in this case, when the steam is impinging tangentially, absolutely, then it will be 0. That the relative velocity itself will be 0. Because there is only tangential component and that itself is 0. Therefore, the absolute velocity at the exit will be 0. Right? Okay. Now, therefore, what is the maximum? Therefore, what is the maximum efficiency? Maximum efficiency is equal to. Now we will put that value, optimum value of rho there. So it will be 2. So
আপনি কি বললেন? আপনি অ্যাবসলিউট ভেলোসিটি 0 হবে না কি একটা বললেন, ওটা বুঝতে পারলাম না তো।
বলছি 1 plus kc multiplied by. Acha. So rho optimum is equal to cos alpha 1 by 2. Therefore, what is the value of that? Rho cos alpha 1 minus rho square. So it is basically rho is equal to cos alpha 1 by 2. Therefore, it is rho into cos alpha 1 is equal to. So it will be basically cos alpha 1 square by 2 minus rho square. What is that? Rho square means cos alpha 1 square. I'm sorry, cos square alpha 1, sorry. Divided by 4. So maximum blade efficiency, I'm sorry, it should be eta B max is equal to two multiplied by 1 plus kc multiplied by cos square alpha 1 by 4. Therefore, it is equal to cos square alpha 1 by 2 multiplied by 1 plus kc. That is the maximum blade efficiency. Okay, this is the condition. Now, so if the blades are symmetrical, that means beta 1 is equal to beta 2. That indicates that C is equal to 1. Therefore, C is equal to 1. So, in that case, eta B max will be equal to cos square alpha 1 divided by 2 multiplied by 1 plus k. Okay. So this is for symmetrical blade. Maximum efficiency for symmetrical blade. This is maximum blade efficiency for symmetrical blade. Okay. Next is if we have smooth blade, that is frictionless blade, in that case for frictionless blades, for frictionless blades, k is 1. Therefore, eta B max is equal to, so it is 2 and this 2 will cancel, therefore it will be cos alpha 1 square simply. So simply it will be cos square alpha 1. Now, therefore, this is the condition for maximum blade efficiency with no friction, that means, and symmetrical blade. That means this is for symmetrical blades with no friction. That means when C is equal to 1 as well as K is equal to 1. Okay. So what is the value? Can you tell for that cos alpha 1 if it is say, if alpha 1 is 20 degree, say, then what is the max? Cos alpha 1 square, cos alpha 1, you have already calculated 0.9397, square of that, how much? 93 3 multiplied by 93. It is about 82%, like that, 82% around, isn't it? Isn't it? How much is this? Hello? Point, sorry, it is about 88. It is about 0.8830. Or it is about 88%. Okay, that means that is the maximum efficiency when you have symmetrical blade and no friction. So in this diagram, it is shown that how the efficiency varies with the blade speed ratio. So here it is blade speed ratio as it is 0. So if it is 0, that means blade has no speed. Blade speed ratio 0 means there is no power at the blade. So obviously the efficiency is 0. Now as the blade speed ratio increases, it is about the value that is 0.47, that is maximum. That means this is drawn with alpha 9, alpha is taken as, alpha 1 is taken as 20 degree. So it is about, you see, 0.47. So at that, it is basically maximum, and the value is about 88%, that you can see. Okay. And with a friction, if you consider a friction value, say K is equal to 0.84, if you can consider, and then you can calculate. With friction, it will be less, definitely. You see that with friction, it is less. But still, you see that with friction or without friction, if I consider a constant friction, then the value at which the optimum speed ratio is same for both. Okay. But the maximum efficiency is different, definitely, because there is a role of K. So that will come to be different. In case of K is equal to 1, that is coming to be 2. In case of K is equal to 0.84, that means velocity, that means friction coefficient, say 0.84. So it will be 1.84. So that will be different, definitely. Means about, say 0.84 means how much it will be. So it will be about, say 16% it will reduce. Okay, in that case. Sorry. So half of that, So it will be about 1.84, and another is 2. So basically, so it is about 92%. Another is about 100. If I consider 100, so it will be about 8%, around 8% around less. So you can calculate that and check. With, say, K is equal to 0.84. You can take a value. Okay, one thing, that is one thing. Another thing is that what is the nature of this? What is the nature of this curve? This is a parabolic curve. And you see that this is the diagram efficiency, or the blade efficiency, and the x-axis is showing the blade speed ratio. So here you can check that this is truly a parabolic curve. that is variation. So this is the equation of a parabola that you can see. So this is the equation of a parabola. Okay. Now as it increases, that means as this increases, therefore what is happening is that during this time the blade speed increases and the efficiency increases, and as the speed ratio increases further beyond this point, then the efficiency drops. So you can see from this relation why it is happening like this. So you see that this is basically, it depends on both, that is alpha 1 as well as rho. So you see that initially when the speed ratio, say alpha 1 is constant. Do you listen? Are you listening? During this time,
Yes, sir. Yes, sir.
during initial phase, that means before the optimum value, that rho cos alpha 1 is increasing. Okay, but the increase of, now you see that this is a fraction, isn't it? Rho is a fraction. So as we means, say for example, say if it is a half, so square of half is how much? Square of half is 1/4, right? So that means during this time when it is say about below half, so cos alpha has a particular value, it is constant. Okay, cos alpha is a constant value. Now during the initial phase when it is below that value, now during this time it is varying linearly, but this is having a square, so it will increase, but the increase of this is more than the increase of this. So ultimately the total quantity will increase. So do you follow this? So let me write it here. Let me rewrite the efficiency equation and explain. Although these may not be important for your examination, but it may be good to understand. So what is that? Efficiency, blade efficiency is equal to 1 plus Kc multiplied by 2 multiplied by rho cos alpha 1 minus rho square. Okay. Now for a particular blade, this is constant. Also, for a particular nozzle, this is constant. Now, therefore, the blade efficiency depends on rho only. Here, when you have that fixed design, it depends on rho only. Now, for this first phase, if I divide it into two phases, if I divide it into two parts like this, then there is a zone on this side, and there is another zone on that side. So in this zone, first half, the increment of this is more compared to the increment of this. Because you see the rho is increasing, so all the quantities are increasing. That we can understand. Both are increasing. The rho is increasing as well as rho square is increasing. But during the first half, the increment of rho cos alpha 1 is more compared to the increment of rho square. That is why it is increasing effectively, because this is this minus this. Therefore, if it increases more than this, then effectively it will increase. Okay. Now, in the second part, okay, it has reached the optimum value based on the cos alpha 1. So it has reached the optimum value. That means now dependence of cos alpha to maximize it or to increment to affect the increment has stopped. Now, therefore, only you see that as rho increases, so this rho cos alpha 1 increment is less compared to the rho square. Therefore, effectively, it will reduce and it will go to 0 at a value when it has, say, it is obviously less than 1, because, for example, the blade speed can never be 1. That we have to understand, that blade speed can never be 1. That means blade can never get a same velocity as that of the steam. Okay, so that is the reason that why it is happening like that. So you can take the value and you can check yourself that why it is happening individually. You can check, so that you can take as an assignment. So you can check, say, cos alpha 1, what is that? I told just for a particular cos alpha 1 is 90. Cos alpha 1 is equal to 0.9397. Now, therefore, as rho, so for example, say take this value. So rho is equal to 0.2 and 0.3, you check. So rho is equal to 0.2 and 0.3. You check what is happening for this. So what is therefore rho square? If it is 0.2, then what is rho square? 0.2. 0.2 into 0.2 means 0.04. And 0.3 into 0.3 multiplied by 0.3, it is 0.09. Okay. So here the increment of this is slower. Now what it will make that one? Cos alpha 1 multiplied by rho. So what will be the value of that rho cos alpha 1? How much it will be? Multiplied by 0.2. 93 into 0.2. কত হবে? 0.1879. 0.1879.
1879.
Exactly. 0.1879. Okay, 9, right. If it is 0.3, 0.2819. 0.2819. Okay, so this is the value. So you see that how much this is increasing. আমি যদি একটা টেবিল বানাই, how much this is increasing.
পছন্দ হচ্ছে নাকি?
দেখো, rho cos alpha 1 for two values of rho, I have taken 0.2 and 0.3. The rho square has changed from 0.04 to 0.09, but rho cos alpha 1 has changed from 0.1879 2.2879 কত বেড়েছে বলো এখানে? কত বেড়েছে এটাতে? এই রো কস ও ডেল্টা 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 অফ রো কস আলফা 1, এটা কত হয়েছে চেঞ্জটা? কত হয়েছে বলো এটা? অ্যাবাউট 0.1, তাই না? অ্যাবাউট 0.1, তাই তো? 0.18 থেকে হ্যাঁ হ্যাঁ এক্স্যাক্টলিটা আমি এক্স্যাক্টলি বলো কত হচ্ছে?
0.094।
0.094, এটা ডেল্টা রো। আচ্ছা, ডেল্টা রো স্কোয়ারের কত ইনক্রিমেন্ট হয়েছে বলো? ডেল্টা রো স্কোয়ারটা কত চেঞ্জ হয়েছে? 0.09 থেকে 0.04, 0.04 থেকে 0.09, দ্যাট মিনস 0.05, তাই না? তাহলে কোনটা বেশি হলো? এটা বেশি হলো। তার মানে এফেক্টিভলি এফেক্টিভলি এফেক্টিভ এফেক্টিভলি কত হচ্ছে? ওই এই যে ডিভিশন ডিফারেন্সটা, এটা কত হচ্ছে? রো কস আলফা মাইনাস দ্যাট মিনস বেসিক্যালি চেঞ্জ অফ, দ্যাট মিনস ডেল্টা অফ রো কস আলফা 1 মাইনাস রো স্কোয়ার, এটা কত হচ্ছে চেঞ্জটা? এই দুটো ডিফারেন্স, তার মানে কত হচ্ছে এটা বলো? 0.044, তার মানে এটা পজিটিভ, তার মানে বাড়ছে, এফিসিয়েন্সি বাড়ছে। এই যে এই কোয়ান্টিটি যদি পজিটিভ হয় তাহলে এফিসিয়েন্সি বাড়বে, কারণ এইটা তো দিস ইজ অলওয়েজ পজিটিভ, এটা তো সবসময় পজিটিভ। এটা কি কখনো জিরো হতে পারে? এটা তো এটার এটার তোমার জিরো তো হতে পারে না। কে যদি ধরো জিরো হয়, ইভেন যদি জিরো হয়, হ্যাঁ জিরো হওয়ার কথা নয়, যদি জিরো হয়, ইন দ্যাট কেস অলসো দিস ইজ ওয়ান, ইট ক্যান নট বি জিরো অর নেগেটিভ, তাই না? তাহলে দিস উইল বেসিক্যালি চেঞ্জ, ইট ক্যান বি ইট ক্যান বি জিরো, ইট ক্যান বি জিরো, তাই না? ইট ক্যান বি জিরো, বাট ইট ক্যান নট বি নেগেটিভ। নেগেটিভ হলে এফিসিয়েন্সি নেগেটিভ হয়ে যাবে, এটা তো নেগেটিভ হতে পারে না। ওকে, তাহলে কি হচ্ছে যে দিস ইজ দ্য চেঞ্জ ইজ বেসিক্যালি, আই এম টকিং অ্যাবাউট দ্য চেঞ্জ অফ দিস কোয়ান্টিটি। এই যে আমি আই এম জাস্ট লুকিং অ্যাট 0.2 and 0.3 of the speed ratio and trying to see that from 0.3 to 0.2 to 0.3, what is happening to the blade efficiency, whether blade efficiency will increase or decrease, that I am trying to see. And we see that the change of blade efficiency is due to this one, and this is positive, therefore blade efficiency will increase, isn't it? Clear or not? The blade efficiency is due to the product of this and this. Now say for example blade efficiency at 0.2 and blade efficiency at 0.3, if এটা এই কোয়ান্টিটিতে তো সবসময় কনস্ট্যান্ট থাকছে, তাহলে এইটা যদি বাড়ে তাহলে এফিসিয়েন্সি বাড়বে, এটা যদি কমে তাহলে এফিসিয়েন্সি কমবে। পরিষ্কার বোঝা যাচ্ছে? Okay, this quantity is constant for a particular blade and particular situation. Now if this quantity is increasing, then the blade efficiency will increase. If this quantity decreases, then the blade efficiency will decrease. It cannot be negative, definitely, but if this is increasing, then this will increase. If this is decreasing, then this will decrease. Okay, now therefore we see that this quantity is increasing, the delta of this is positive, therefore this quantity is increasing, therefore efficiency will increase during the first time. Okay, therefore efficiency will increase.
ফস আলফাটা মানে আপনি যেটা বললেন যে রো কস আলফাটা প্রথম 0.4 মধ্যে ইনক্রিজ করছে, মানে রো স্কোয়ারের থেকে গ্রেটার হচ্ছে, তো এইটা কি করে বোঝা যাচ্ছে?
এটা তো ওই যে এই দেখো, এটা কি করে বোঝা যাচ্ছে, মানে এই যে আমাদের অপটিমাম ভ্যালুটা বেরিয়েছে, অপটিমাম ভ্যালুটা বেরিয়েছে তো কস আলফা টার্মসে, So cos alpha is a deciding factor for the optimum blade speed ratio. Cos alpha is playing a role. Optimum value of this is cos alpha by 2, cos alpha 1 by 2. So that is actually playing the role. So that is why up to this value it is এই যে cos এটাই তো ভ্যালু, এই যে কত, এটা 0.47 বেরিয়েছে তো।
হ্যাঁ 0.47।
হ্যাঁ ওই তো অপটিমাম ভ্যালু কত বেরিয়েছে 0.47, তার মানে এর নিচের ভ্যালু হলে এটা বাড়বে, এর নিচের ভ্যালু হলে এটা বাড়বে, এর পরের ভ্যালু হলে এটা কমবে। ওই cos alpha 1 এখানেই তোমার যা রোল প্লে করার করেছে, এই যে cos alpha 1 by 2 এসছে, বোঝা যাচ্ছে? এই যে দ্যাট ইজ রো অপটিমাম ইজ ইকুয়াল টু cos alpha 1 by 2. So during the calculation that dependence is reflected here. So you see from this diagram that before this value or below this value of cos alpha 1, or that cos alpha 1 means basically cos alpha by 2 is the optimum blade speed ratio. So this is that value, optimum blade speed ratio. Now below this value, this is again, this is cos alpha by 2. So this below this value the efficiency will increase, and after this value the efficiency will decrease, because you see that that was 0. You see the differentiation of that was 0. So rho cos alpha 1 minus rho square, differentiation of that was what? Cos alpha 1 minus 2 rho. So that was 0. Therefore rho was cos alpha 1 by 2. So up to that value it will increase, then it will decrease. এই যে তুমি যদি এই কার্ভটাকে ডিফারেন্সিয়েট করো, তাহলে কি হবে? এখানে ম্যাক্সিমাম ভ্যালুর জন্য তোমার স্লোপটা 0 আসবে না? তারপরে তো এদিকে গেলে আবার নেগেটিভ হতে শুরু করবে, মানে কি এটা ডিক্রিজ করছে ওই কোয়ান্টিটিটা। তার মানে এই যে কোয়ান্টিটিটা, এই কোয়ান্টিটির যে স্লোপটা, এই কোয়ান্টিটি, এই যে চেঞ্জটা, এই চেঞ্জটা 0 হতে শুরু করবে। আমার কি বেসিক্যালি এই যে এই কোয়ান্টিটি, মানে কি এই কোয়ান্টিটিটাই তো বেসিক্যালি ডিটারমাইন করছে, দিস কোয়ান্টিটি ইজ ডিটারমাইনিং whether the slope will be positive or negative, right? Now as this is the maximum value when it is 0, that means the change of that is 0 here. Therefore up to this it will increase, and after that it will decrease. Which quantity will decrease? This quantity. That means change of that quantity, এটা দেখো এই যে চেঞ্জ অফ দ্যাট কোয়ান্টিটি, সেটাই তো আমরা ক্যালকুলেট করছি না। এই যে চেঞ্জ অফ দ্যাট কোয়ান্টিটি, এই যে ডেল্টা অফ কস আলফা, এই ডিফারেন্সিয়েশন মানে কি বেসিক্যালি, যে আমরা যে করছিলাম না, যে ডি ইটা বি অফ বাই ডি রো। সো এই যে ইটা বি, দ্যাট মিনস কি এটা বেসিক্যালি কি ডেল্টা অফ ইটা বি, তাই না? ডেল্টা অফ ইটা বি বাই ডেল্টা অফ রো, লিমিট আন্ডার লিমিট ডেল্টা রো টেন্ডিং টু 0, তাই না? এই যে ডেল্টা অফ ইটা বি, দ্যাট ইজ নাথিং বাট হোয়াট? ডেল্টা অফ 2 1 প্লাস কেসি ইন্টু rho cos alpha 1 minus rho square, isn't it? Because this is eta b, and we know that for a particular blade, this quantity is constant. This quantity is constant, so it will come out. Therefore this delta quantity is equal to, therefore it is equal to 2 1 plus kc multiplied by delta of rho cos alpha 1 minus rho square, isn't it? Now তাই তো আমরা এটাই ক্যালকুলেট করছিলাম, এই যে এটা। তার মানে কি এই যে কার্ভটা ক্যালকুলেট করলাম, এটা তো এফিসিয়েন্সির ইনক্রিমেন্ট বা ডিক্রিমেন্ট, দ্যাট উই ওয়ার ক্যালকুলেটিং।
ইনক্রিজ করছে,
এফিসিয়েন্সিটা পজিটিভ, মানে চেঞ্জ অফ এফিসিয়েন্সিটা পজিটিভ, তার মানে এফিসিয়েন্সি ইনক্রিজ করছে। বুঝা গেল? আচ্ছা, এরপরে দুটো ভ্যালু এরকম নেবে, you take two values, say 0.7 and 0.8, রো ভ্যালু 0.7 and 0.8। সেখানে দেখো একটু পড়ে দেখা যাক তাহলে আমাদের ইয়েটা, দুটো ভ্যালু নিই। রো is equal to say 0.7 and 0.8। আমরা দেখি কি হয়, আমরা একটু মাঝখানে একটু দাগ দিয়ে নিই, তাহলে সুবিধা হবে। আচ্ছা, তাহলে তাহলে রো স্কোয়ার কত হচ্ছে গো? 0.7 এর স্কোয়ার মানে 0.7 ইন্টু 0.7 মানে 0.49, তাই না?
0.14, হ্যাঁ 0.49, 49,
0.949 তো। হ্যাঁ, আর 0.8 হলে
আচ্ছা
0.64।
0.64।
0.64। আচ্ছা আচ্ছা, এবারে রো কস আলফা ওয়ান এর ভ্যালুটা কিরকম হচ্ছে দেখি। রো কস আলফা ওয়ান, এই ভ্যালুটা কত আসছে ওটা করে বলো। ওই পয়েন্ট যেটা ছিল তাকে গুণ করো, 0.9397 মাল্টিপ্লাইড বাই পয়েন্ট একটা সেক 0.7, এটা হচ্ছে 0.6578। 0.6578, আর একটা হচ্ছে 0.8 দিয়ে মাল্টিপ্লাই করলে 0.7518। 0.7518, তাই তো? এবার তাহলে আমরা ওই ডেল্টা অফ দ্যাট ক্যালকুলেট করি। এখানে ডেল্টা অফ রো কত হলো?
ইনক্রিমেন্ট করে গেল তো,
ইনক্রিমেন্টই করলাম।
ইনক্রিমেন্ট হয়ে গেল।
আরে হোক না, কিসের ইনক্রিমেন্ট হয়ে গেল?
এর রো কস আলফা আছে আর
ডেল্টা রো কত
ইউজ
হচ্ছে?
করেছে,
ডেল্টা রো
হ্যাঁ
কত হচ্ছে?
ঠিক 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 আছে।
ডেল্টা রো কত হচ্ছে এটাতে? সে একই 0.1।
হ্যাঁ
আচ্ছা,
0.1।
ডেল্টা রো স্কোয়ার কত হচ্ছে? কত হচ্ছে? 0.15, না সরি,
0.15,
হ্যাঁ 15। আচ্ছা,
হ্যাঁ।
একটুখানি দাঁড়াও। আচ্ছা, তাহলে এটা কত চেঞ্জ হচ্ছে বলো? আলাদা করে আমরা নাও করতে পারি, এটা ক্যালকুলেট করে দেখি কত হচ্ছে। কত হচ্ছে এটা? ডেল্টা অফ রো কস আলফা ওয়ান কত হচ্ছে গো এটা? ডেল্টা অফ রো কস আলফা ওয়ান এটা কত হচ্ছে?
0.094।
0. বাড়ছে তো?
09, হ্যাঁ বাড়ছে, হ্যাঁ।
বাড়বে। 0.094। আচ্ছা, একটুখানি।
আর এখানে আপনার ডেল রো কস কস আলফা ওয়ান মাইনাস ডেল রো স্কোয়ার, এটা নেগেটিভ আসবে।
দেখো, হ্যাঁ ওইটাই বলছি এবার, তার মানে দেখো এই যে
নেগেটিভ, আচ্ছা তোমরা
ডেল্টা
নেগেটিভ
রো
করছো।
স্কোয়ার যেটা, সেটা বেশি না? ডেল্টা রো স্কোয়ারটা বেশি তো।
আচ্ছা
তার মানে আমার
ঠিক
এই যে
আছে।
সেকেন্ড কোয়ান্টিটিটা এখন বড় হয়ে গেছে, আগে সেকেন্ড কোয়ান্টিটিটা কম ছিল কম্পেয়ার টু দিস, এখন সেকেন্ড কোয়ান্টিটিটা বেড়ে গেছে। দেখো ওই এই ভ্যালুটা একই আছে, 0.094, এটা একই আছে, আগেও পয়েন্ট জিরো
হ্যাঁ
নাইন
আপনার
ফোর
ডেল
ছিল।
রো স্কোয়ারটা বেড়ে গেছে।
হ্যাঁ, আগেও একই ছিল, কারণ কি আগে এটা তো লিনিয়ার ভ্যারিয়েশন হচ্ছে না। এই যে রো কস আলফা ওয়ান সেটা তো বেসিক্যালি ওই ডেল্টা রো ইন্টু কস আলফা, মানে 0.1 দিয়েই মাল্টিপ্লাই হয়েছে এটাকে। তাহলে 0.1 দিয়ে মাল্টিপ্লাই হলে ওই 0.93 হবে, এটা আমাদের ক্যালকুলেট করে না দেখলেও হতো। হ্যাঁ, মানে এটা এটা কি ছিল বেসিক্যালি? কস আলফা ভ্যালু কত ছিল? কস আলফা ওয়ান
হ্যাঁ
এটা হচ্ছে 0.94 ছিল তো, প্রায় 0.9397। তো এইটাকে আমি যদি 0.1 দিয়ে মাল্টিপ্লাই করি, সেটা ওই 0.94ই
হ্যাঁ
আসবে,
হ্যাঁ,
এটাই আসবে।
সেমই আসবে, সেমই
হ্যাঁ,
আসবে,
তার মানে
সেমই
ওই
আসবে।
ভ্যারিয়েশনটা দেখো লিনিয়ার, ওটা হচ্ছে লিনিয়ার ভ্যারিয়েশন।
হ্যাঁ
আর এইটা হচ্ছে নন লিনিয়ার ভ্যারিয়েশন। প্রথমবারে দেখো নন লিনিয়ার ভ্যারিয়েশনটা এটা এটার দিকে কিন্তু যতটা বার ছিল এদিকে, এই যে এইটা এটার থেকে কম ছিল না, এটার থেকে বেশি ছিল। তার মানে কি এই দিকে ইনক্রিমেন্টটা বেশি ছিল। আর এইখানে কি হচ্ছে? এখানে এই রো স্কোয়ারের ভ্যালুটা, ডেল্টা রো স্কোয়ার, এটা বেশি হয়েছে দেন দিস। তার মানে ওইটা এমন একটা অপটিমাম ভ্যালু যার পরে গেলে নেগেটিভ কোয়ান্টিটিটা বেশি বাড়বে কম্পেয়ার টু দ্য পজিটিভ ইনিশিয়াল কোয়ান্টিটি। তাই জন্য ওটা এফেক্টিভলি দুটোর রেজাল্ট্যান্ট হতে
এক্সারসাইজ জিজ্ঞেস করুন।
রেজাল্ট্যান্ট হয়ে
ঠিক
সেটা
আছে।
কমে যাবে। ঠিক আছে?
মাঝখানে ওটা থাকবে অপটিমাম
হ্যাঁ,
ভ্যালু।
একদম তাই। মানে এমন একটা অপটিমাম ভ্যালু যে ওই দুটোর ব্যালেন্স হয়ে গেছে। হ্যাঁ, মানে কমা আর বাড়া দুটোই
হ্যাঁ
ব্যালেন্স হয়ে গিয়ে ওখানটায় অপটিমাম হয়ে গেছে। প্রথমে এবার হচ্ছে কি কম
অপটিমাম।
ছিল, একটা একটা ইনিশিয়ালি দ্যাট উইল ইনক্রিজ। ওকে, after that point it will decrease, and at that value it is balanced, and this is the optimum value.
ওটা ম্যাক্সিমাম ভ্যালু।
Or for that it is the maximum efficiency. So therefore this delta of rho cos alpha 1 minus rho square, what is that? Therefore 0.094 minus 0.15, so it is about minus 0 point কত আসছে?
0.56।
0.56, তাহলে এটা নেগেটিভ, তাহলে this is negative, so efficiency will decrease. Will decrease for this change of rho from 0.7 to 0.8. Okay, so that is the basically explanation behind this for this. So it is like a parabola, means it is a parabola in fact. So it is a parabolic variation, and it will have a maximum value. So the maximum value corresponds to this optimum value. Now for uh, zero angle of that means zero angle of the nozzle, that means if alpha 1 is 0, then it will be basically half, simply half. Because you can see that it is cos alpha by 2, that means 1 by 2, it is half. So the blade speed will be half of the steam speed, and in that case the it will leave with basically, as you see that it is going with uh, the velocity v, and as the relative velocity will be remaining zero, relative velocity will remain same. So at the exit, if it is leaving with 90 degree, then it will be basically 0. For maximum efficiency it is to be 0, and as the what is the efficient, basically what is the relative velocity, তোমার এখানে একটা কোশ্চেন ছিল না, কেন 0 হচ্ছে, কি বলছিলে না?
তো ওটা আপনি কি বলছিলেন যে অ্যাবসলিউট ভেলোসিটি 0 হবে, ওটা কি এটা বলছিলেন না? ওটা বলছি।
হ্যাঁ, বলছি।
হুম।
হ্যাঁ, ওই ভ্যালুটা, ওটা ওই ছবিটাকে আরেকটু তুলে আনি। হ্যাঁ, ঠিক আছে। কি বলছিলাম, যে if the steam is impinging on the blade at parallel to, that means in the tangential direction, then from the condition we have seen that this is v by 2. Okay, now say for a frictionless blade we know that relative velocity will be same, that means vr1 will be same as vr2. তো ঠিক, এটা তো জানো, এটা তো বোঝা যাচ্ছে নাকি? ফ্রিকশনলেস হলে এটাই হবে, ঠিক আছে। আচ্ছা, ইনলেটে what is the velocity, relative velocity, what is vr1? V1 মাইনাস ইউ, তাই না? আর এক্সিটে কত হবে? VR2 এক্সিটে কত হবে?
V2 প্লাস
হ্যাঁ, V1 মাইনাস ইউ, আর এটা কত হবে? V2 V2 প্লাস ইউ। So they should be same. So V1 minus u is equal to V2 plus u, তাই না? তাহলে কি হচ্ছে? তাহলে V1 is equal to V2 plus 2u, তাই তো? তাই না? আবার আমরা কি জানি যে এই V1 is equal to 2u, এই তো এফিসিয়েন্সি, ম্যাক্সিমাম এফিসিয়েন্সির জন্য বার করলাম, তাই না? ফর ম্যাক্সিমাম এফিসিয়েন্সি, ফর
V1 to U.
ফর ম্যাক্সিমাম এফিসিয়েন্সি, ম্যাক্সিমাম ব্লেড এফিসিয়েন্সি, V1 is equal to 2u, or একটু প্রপারলি লেখা উচিত, that is u is equal to v by basically that. So u is equal to v1 by 2, এটা লিখেছি অবশ্যই, v1 by 2, that means basically v1 is equal to 2u। তাহলে এখানে v1 is equal to 2u বসিয়ে দিলে v2 is equal to 0 আসছে, ওপরের ইকুয়েশনে দুটো ইকুয়েশনকে কম্বাইন করে। therefore from these two equations, এইটা জেনারেল ইকুয়েশন, this is general equation, এটা হবে সবসময়, ম্যাক্সিমাম হোক বা নাই হোক, এটা হবেই সবসময়। আর ম্যাক্সিমাম এফিসিয়েন্সির জন্য কি হবে? এটাই হবে। ফর ম্যাক্সিমাম এফিসিয়েন্সি, blade efficiency, therefore, so if I put this combining these two equation, it will be 2u is equal to v2 plus 2u, therefore v2 is 0. So here what is the consideration? Consideration is that v2 is also leaving tangentially, that means in that case tangentially the tangential component is 0. That means entry as well as exit both are tangential. So basically the meaning is that the meaning is that the tangential component for maximum blade efficiency is 0. That is the meaning. Okay, ultimately that is the meaning. So tangential blade velocity, tangential steam velocity or fluid velocity, steam say, steam velocity, tangential means whirl velocity, tangential or whirl, tangential steam velocity at the exit, absolute, এটা absolute, huh? Exit from the blade is 0 0 for maximum blade efficiency, তাই না? ক্লিয়ার? বোঝা গেল? ঠিক তো?
তাহলে এখানে অ্যাবসলিউট ভেলোসিটি জিরো হচ্ছে মানে টেনজেন্সিয়াল ভেলোসিটি।
হ্যাঁ, ওই অ্যাবসলিউট ট্যানজেনশিয়াল কম্পোনেন্ট, তার মানেটা কি? মানেটা হচ্ছে এই যে যদি ও কোনো ট্যানজেনশিয়াল কম্পোনেন্ট নিয়ে বেরোয়, the meaning is that if the steam exits from the turbine blade with some tangential component, that means we have still something that we have not tapped or captured or used. মানে ওই ব্লেড ভেলোসিটিটা আমরা এখনো ইউজ করতে পারিনি, ওই ভেলোসিটিটা নষ্ট হলো না। ওই যে ট্যানজেনশিয়াল কম্পোনেন্টটা তো আমাকে
আচ্ছা
পুরোপুরি ইউটিলাইজ করতে হবে।
আচ্ছা
That means if the steam is exiting with some tangential component of velocity, non-zero tangential component of velocity, that means we have not utilized its full tangential capacity. কারণ কিছুটা আনইউজড থেকে গেছে এখনো, তার মানে হচ্ছে তাই। তার মানে কি, যখন যখন ম্যাক্সিমাম ভেলোসিটি হবে, ফর ম্যাক্সিমাম ভেলোসিটি all the tangential velocity that has been utilized, and the steam will exit with alpha 2 is equal to 90 degree. That means, so it is another way, এগুলোতে ধরো এমসিকিউ টাইপের আসতে পারে কোশ্চেন, যে ফর ম্যাক্সিমাম বেলোড এফিসিয়েন্সি what is the steam exiting, what is the angle at which the steam is exiting from the, or absolute angle, that means alpha 2 is equal to 90 degree. Therefore alpha 2 will be 90 degree. That means এটা তো আমরা ট্যানজেনশিয়াল ধরেই নিয়েছি। That means if there is some other angle of the blade and the steam entering and leaving at some other angle, then tangential component will be zero, and other component, that means axial component, there will be positive axial component, and that will be basically only axial component. So for other blade angles. এখানে আমরা কি ধরেছি, ব্লেড অ্যাঙ্গেল জিরো জিরো ধরেছি দুটোই, এটাতে দুটোই জিরো ধরেছি, বিটা ওয়ান বিটা টু দুটোই জিরো ধরেছি। এখানে ফর দিস কেস বিটা ওয়ান ইজ ইকুয়াল টু বিটা টু ইজ ইকুয়াল টু জিরো। ফর আদার অ্যাঙ্গেলস অফ বিটা, beta 1 beta 2 non-zero. In that case alpha 2 is basically 90 degree. ঠিক আছে, বোঝা গেল?
জিরো হয় দুটোই, তাহলেও তো 90 ডিগ্রি হবে।
জিরো হলে তো কোনো ভেলোসিটি থাকবে না, জিরো হলে তো একটাই
তখন
ভেলোসিটি,
অ্যাঙ্গেল কম্পোনেন্ট থাকবে।
জিরো হলে তো একটাই কম্পোনেন্ট, তো ভেলোসিটি থাকবে না, তো এদিকে তো কোনো আর কোনো ভেলোসিটি নেই। এটা যদি জিরো হয় তাহলে তো রিলেটিভ ভেলোসিটি আর এর একই দিকে হবে না, তখন তো এইটা যে
কম্পোনেন্ট সব জিরো হয়ে যাবে।
হ্যাঁ পুরোটাই জিরো, মানে এটা তো
বি1 বি2।
এটা অ্যাবসলিউট ভেলোসিটি নিয়ে ঢুকছে, এটা অ্যাবসলিউট ভেলোসিটি আর রিলেটিভ ভেলোসিটির ডাইরেকশনটা তো একই, কিন্তু এটা তো জিরো ভেলোসিটি নিয়েই বেরোবে তখন, মানে এটা অলমোস্ট কিছুই থাকবে না, ভেলোসিটি পুরো ডেড হয়ে যাবে আর কি। মানে কোনো
ওটা বেরোবে না,
হ্যাঁ,
ওটা বেরোবে না, হ্যাঁ।
বুঝা গেছে,
কিছু থাকবে না।
কিছুই থাকবে না। এবার মানে ওটা গ্র্যাভিটির জন্য যদি কোনো অ্যাকশন, গ্র্যাভিটির কোনো মানে রোল থাকে, গ্র্যাভিটির জন্য ওটা ড্রপ বাই ড্রপ পড়ে যাবে, মানে এটা এখান দিয়ে ঢুকবে, কিন্তু এখানে এখানে গিয়ে জিরো ভেলোসিটি হয়ে যাবে, এবার বেরোনোর কোনো আর ক্ষমতা থাকবে না আর কি। মানে ও এবার ড্রপ বাই ড্রপ, ও গ্র্যাভিটির জন্য আন্ডার গ্র্যাভিটি ইট উইল ফল লাইক দ্যাট, তো ইট উইল হ্যাভ নো ফ্লো at the exit. বোঝা গেল?
আচ্ছা,
ঠিক আছে, তাহলে এবার খাওয়া দাওয়া করে নাও নাকি? খাওয়াইনি তো, না হয়েছে?
হ্যাঁ, তাহলে
ঠিক
হয়ে
আছে,
গেছে
ঠিক আছে,
খাওয়া।
ভালো হয়েছে। আর কি ক্লাস করবে নাকি?
চাপ না হয়েছে?
না, আমার একটু দেরি
তাহলে
আছে।
কালকে করাবেন তাহলে আবার।
হ্যাঁ,
ও আচ্ছা আচ্ছা, ঠিক আছে তাহলে কালকে করাবেন আবার, একটু কালকে, কালকে আবার ক্লাস করবেন না হয়?
ঠিক আছে, ঠিক আছে। আরো দুটো
ঠিক আছে।
দুটো পড়ানোর ইচ্ছে ছিল আজকে, কিন্তু এটাতে একটু এলাবোরেট ডিসকাশন হলো, ঠিকই আছে।
ঠিক আছে রে, ভালো হলো।
হ্যাঁ, বোঝা গেছে তো পুরোটা?
হ্যাঁ, ঠিক আছে।
ঠিক আছে,
ঠিক
এবার
আছে।
একটু লিখে নেবে, নোটটা লিখে নেবে নিজে নিজে।
আচ্ছা।
পুরো যা ডিসকাশনটা হলো, রেকর্ডিংটা শুনে ওটা নোটগুলো নিজে নিজে লিখবে, তবে হবে। পুরো পুরো যা যা এক্সপ্লেনেশন হলো সেই পুরো এক্সপ্লেনেশনটা।
হ্যাঁ স্যার, রেকর্ডিংটা আমি করে নিয়েছি এবার।
আচ্ছা আচ্ছা।
ঠিক আছে।
ওকে ওকে।
পরে আমি শুনতে পারি আবার আমরা
ঠিক
কথা।
আছে, হ্যাঁ হ্যাঁ ঠিক, আমি অবশ্য রেকর্ডিং গুলো আপলোডও করে দিই। হুম। ঠিক আছে।
হ্যাঁ, তাহলে তো ঠিক আছে।
ঠিক আছে।
ঠিক আছে, গুড নাইট স্যার।
গুড নাইট, গুড নাইট। হুম।
আচ্ছা।